welcome back to Risc-V emulation in a high-level language. This is going to be the third and final session before we actually start getting into the meat of actual Risc-V machine code, but I wanted to dispatch this particular topic before because it's useful and important to have it in the back of your mind as we approach the emulation. So let's switch over to the coder or the code environment, and we're going to discuss encoding. And encoding is important for many reasons, but it is almost magic. It's the thing that makes the chunk of silicon that is inside of your computer actually perform things like rendering video or letting you play a game or edit a document. And yet, at the very bottom level, it's just electrons moving around in transistors on a chip. So we bow our heads in admiration to the electrical engineers who made this all possible, but it's hopeless to reason about a running program at the level of electrons, so we have to start by building abstractions. And the first one you already are familiar with. You should be familiar with the binary system, where numbers are represented as binary encodings. So, for instance, you'll have a number like 00 that would represent the number 00. The bit pattern 01 in binary is the number 1. The bit pattern 10 is equal to 2, and finally 11 is equal to 3. So this is an example of an encoding. We use two binary bit digits, 1 and 0, to encode 4 different values. But this is not the only possible encoding of numbers with bits. For instance, you could use the gray code. Now, gray code looks like this. You have 00 representing 0, 01 representing 1, but then flipping only one bit, you get the pattern 11 for the number 2, and finally 10 for the number 3. So this is a completely valid encoding for these numbers called gray encoding, and it's actually quite popular and used by electrical engineers when a transition between two adjacent numbers should only result in the flipping of one bit. And as you can see, in this case, you get 00, 01, and then you transition from 1 to 2. There's only one bit flipping, in contrast to the binary encoding where you get 2 bits flipping, this one from 1 to 0 and the other one from 0 to 1. So encodings are arbitrary. Your computer doesn't really care, but you care, you the programmer, you the user, because the encodings represent more abstract notions that are important to you in your program. So the raw bit patterns will be flowing through your through the transistors in your CPU, but it's the program itself that decides what the meaning of those bits are going to be. So in some programs, these bits will represent various things. For instance, one of the more common uses of bits is to represent text, and the most popular, I would claim, representation is characters being represented in ASCII. So ASCII is a symbology, if you want to use a symbology, if you want to be fancy. It's a way to represent the letters of the English alphabet and a bunch of other symbols as binary bit patterns. So, for instance, if you wanted to represent the lowercase a character in ASCII, well, you would use the following bit pattern. Now, this is just a convention, and ASCII is not the only character encoding that has been devised. For instance, IBM devised EBCDIC back in the 60s as a way to represent text, and it looks completely different. And if you're familiar with the Sinclair ZX81, very popular British micro from the 80s, it had its own encoding of letters, which is not similar to ASCII. So it's a convention, and these conventions permeate everything that we do in programming. We have conventions on what bit patterns are used to represent numbers, just like we discussed here. And we have bit patterns for text, we have bit patterns for color, for sound, for video. There are all kinds of encodings. So as a low-level programmer, an assembly language programmer, you get very, very involved in encodings. It's important to keep in mind that when you are in assembly language, the assembly language will allow you to interpret any bits any way you want. It is your program that decides what the interpretation is. So a bit pattern, a bunch of bits stored in a register, it could be anything, but your program decides how that interpretation is to be done. So in order to print our numbers in binary, we're going to use this method convert to int32 or sorry to string and pass in a base. If I use this trick, I can now represent integers as their underlying bit pattern on this computer. So you'll see here how the original hexadecimal number has been re-rendered as a string of binary bits. Now, why am I talking so much about coding? Well, it turns out that a Risc-V instruction, just like any other machine code instruction, is just another encoding. It encodes the instruction, which is this part, and then it encodes the operands in some well-defined way that the Risc-V manual specifies. So this is all well and good, but our emulator needs to be able to locate those pieces of the encoding out of the underlying bit patterns and then interpret them in ways that match the specification of the Risc-V instruction set. So we need to learn how to manipulate bit patterns, extract them out of words, and also maybe assemble them into words, because this assembler here is going to be performing that job for us. It's going to take these arguably human readable instructions and turn them into 32-bit words, which are going to be actual encodings for the instructions that we want to execute in our emulator. So we have to become familiar with bit patterns. And we also have to become familiar with a very important way to represent numbers, which is used widely in computing. But again, it's not a unique encoding. There are many possible encodings, but the encoding that I'm referring to is how we encode negative numbers. Let's take this example here with the bits. Let's add another extra bit so that we have 8 possible values. So we have the original 4 values, and then we're going to add 4 more, and we're going to give their equivalents like this in binary. Now, you'll notice that in this sequence of numbers, there's no way to represent any negative numbers. And how would we do that? Well, we would choose a different kind of encoding. And this other encoding basically says that if you have a negative number, what you want to do is take the bitwise inverse of that number and add 1. That's just a rule. It's just an encoding. So if I wanted to represent -1, which is 0001, the rule is flip all the bits, so we get a 1, 1, 0 instead of 0, 1, 1, and then add 1. And from now on, this number is considered -1. Okay, and then for -2, well, we do the same thing. We take 0, 1, 0, we flip all the bits, so we get 1, 0, 1, and then we add a 1. Now, if you remember your binary arithmetic, 1, 0, 1 plus 1 is 1, 1, 0, and that is -2. And you can go on doing this until you get to -3 and, oops, yeah, 101, and then finally 100. So notice now that Depending on whether these 3 bits are to be considered a signed or an unsigned number, I can either get a numeric range from 0, 1, 2, 3, and then 4, 5, 6, 7, or I can get the numeric range -4 through -3, -2, -1, and then through 0, 1, 2, 3. It all depends on my interpretation. Again, it's the program that decides how these numbers are interpreted. The numbers by themselves are just bit patterns. They have absolutely no meaning. So now this is important for us because we want to represent positive and negative numbers in computers. It's important to be able to say that the temperature is negative, or we want to perform a subtraction by addition. And so this is our way forward. We decide that in particular cases when we are representing negative numbers, we use these bit patterns where we've decided that negative numbers are just their positive number with all the bits flipped and then added with 1. This particular representation is known as 2's complement representation, and it is probably the most popular representation system for signed numbers on computers, although there are others. We might get into those later in the series. Alright, so now that we know how to represent negative numbers, we can start looking at how to extract bit patterns and build bit patterns. And in order to do that, we're going to erase our Scratch program and move back to C# for a little while. So let's get rid of this code, and let's get rid of this expositionary material. We won't need the emulator this time, or at least not yet. And what we're going to do is we're going to do a bit pattern extraction. So here is a bit pattern. It's an unsigned integer, which means that I'm treating this following variable as a bunch of bits. And let's use the bit pattern 1, 0, 1, 0, 1, 0, 1, like this. Alright, so here's a bit pattern, and suppose I wanted to extract the lowermost 4 bits out of this. So to do this, what we're going to do is we're going to create something called a mask. And a mask is just a number, a bunch of bits, where the bits that we want to keep are 1 and the bits that we want to discard are 0. So if I wanted to keep the lowest 4 bits of this number, I would write this mask. And then we're going to use the AND logical operator. So we'll say uint result equals the number and then ANDed with the mask. Now you should be familiar with the AND binary operator. What it does is just take the logical AND and returns a bit that is set only if both of those 2 bits are set. But if either one of them is 0, then the result is going to be 0. So now if we print out the result of this combination, we expect 0, 1, 0, 1, the last 4 bits to shine through, but the first 3 bits will be ignored and will be zeros. So we should see, as a result, 0, 1, 0, 1, 0, 1. Let's verify this by running our program. And there it is. Now the leading 0 is elided because we haven't told how wide our bit field is. We could specify that by adding a 7. And of course that's not going to work because it's the convert function that is actually responsible for that. But let's not worry about that for now. Just remember that that leading 0 was elided by the convert to string function, but it just means that there's no bit on bit position 3 from the start of the word. Okay, good. So what if we wanted to extract the top 3 bits? Well, we change the bit pattern to 1, 1, 1, 0, 0, 0, and now we should get 1, 0, 1 again, but this time it's the bit pattern, sorry, we're going to get 1, 0, 0, 1, but then a bunch of zeros at the end, because those are the ones that get masked out by this mask. But now my new requirement is that I want these 3 bits, but I don't want them scaled like this. I want to get rid of those 3 or those 4 zeros. And to do that, what we're going to do is we're going to use the shift operation. And this is where signedness and unsignedness becomes important. But let's start with this example. We're going to shift those bits by 4 bits now. We want to get rid of these 4 bits, so the shift operator will move all of these bits, and the direction is to the right. This is the right shift operator, so we're going to move those bits to the right, and the end result should now be 0, 1, 0, 1. Or 0, 0, 1, 0. Oh, no, 0, 1, 0, 1. There we go. So let's run that. And there we go. So what we did was we got those 3 bits and we shifted them to the right by 4. And naturally, if you have a right shift, there should be a left shift. And so what we can do is take our result, and then we can shift it to the right by 1, for instance. And what should end up happening then is that we should get a 0 shifted in from the right side. So all these bits will move 1 step to the left, and then you have to decide what happens with the newly exposed bit position. And when you shift left, the bit that gets shifted in is going to be a 0. So the end result should be 1, 0, 1, 0, or 10 if you're thinking in decimal. And if we run this, there it is, 1, 0, 1, 0, our number in decimal. Now, recall that we talked about signed numbers before. You might have noticed that all of the signed numbers had this in 2's complement. All the negative numbers had this property that their most significant bit, the highest most bit, is a 1. So what we're going to do is going to change our data type to a signed byte. This is a C# data type that is treated by the compiler as a signed number, and the .NET runtime will treat it as a signed number, and the CPU that I'm running it on will treat it as a signed number. And that means that one of the things it means is that the high bit is determining whether this number is treated as a negative number or not. So let's write the -1 in as a signed byte. Now remember, bytes on this computer are 8 bits, so we need a 1 that consists of 8 bits, which is this, and then we flip all the bits, so all the zeros become ones, all the ones become zeros. And then finally we add 1, and now we have a signed byte. Now the compiler is now complaining because 255 cannot be converted into a signed byte. And the reason for that is that this actually is an unsigned byte, or rather a number that will not fit in a negative signed byte. So what we have to do here is just tell the compiler, I know what I'm doing. And then we can say, convert this to the bit pattern of all ones. Okay, great. Now let's try shifting that to the left by 1 step. So we'll take our number and we'll shift it by to the left by 1. And here's a peculiarity of the C# compiler. The C# compiler, when it compiles an arithmetic instruction like this, it promotes the number, the result, to an integer, a signed integer. So what we need to do is cast this back down to a signed byte. And we get this. All right. So now if we print this out, let's see what happens. So here again, the C# compiler took my signed byte, and notice what it did. It extended the number of ones. So there's a lot more ones than the eight ones that we started with. And this is because convert to string I think it doesn't have an overload for signed bytes, so it will find the closest one, which is a signed short. So this number here is 16 bits, a signed short number. But notice how the 0 got pushed into the least significant digit here when we shifted by 1. So what is this number? If we interpret this as a negative number, it turns out that this is -2. So what this amounts to is actually a multiplication by 2. And in fact, this is how many computers and many programs perform simple multiplications of powers of 2. All you have to do is shift by the number of bits that you want the number to be shifted, and that corresponds to the number of zeros in a binary number. So for instance, a multiplication by 2, well, 2 is represented as a 1, 0. So count the number of zeros. There's 1, 0. So that means that if I want to multiply by 2, I just inject 1, 0. If I want to multiply by 8, that's the binary representation is 1, 0, 0. In order to perform a multiplication, I'm sorry, this is 8. This is 8. To multiply by 8, you shift by 3 digits. So if I wanted to multiply this negative number 1 by 8, I would shift it to the left by 3. And so now if I run this, you will see a bit pattern, but let's also print out this number in hexadecimal. And then we get rid of this x. It doesn't really give us any value. So notice how this number, 111110, became FFF8. Well, so what is FFF8? Well, it is -8. If I add 8 to this result, it becomes 0. So something that gets added to 8 results in 0. That must be -8. Okay, so we see now how left shifting multiplies by 2. Well, what does right shifting do anything similar? Let's use a nice unsigned number to begin with. We'll start with the number 5. And let's shift it by 1 step. Like this, and then 2 steps, and then 3 steps. Let's see what that does. So careful with copy and paste. So shift it by 1, shift it by 2, shift it by 3. What will the result be? And what happens is that the digits are pushed to the right. So, hold on a second. Oh yes, they're printed in binary. So this is actually 0, 1, 0. So what we did was we shifted this to the right, which means that the 1 at the end gets thrown away, and then we're ending up with this 0, 1, 0, which convert to string is trimming off the leading zeros from. And then similarly, if we shifted by 2 bits, then this is our result now. We'll get 0, 1, which is represented here without the leading 0. And finally, when you shift it 3 times, you get 0. Now, if you're looking a little closer at this, you might think of this as it's almost like division by the corresponding powers of 2. This left or right shift by 1 is just the same as taking my 5 and dividing by 2. Except, of course, I don't get 1.5. I'm discarding the low bits. So this is more like take the quotient of the number with a power of 2, but then discard the fractional part. Okay. So now the exciting part comes when we start using right shifts on a negative number. So Let's, in order to stop fighting the compiler, let's just define the number n to be -1. So this number is going to be 32 ones because integers in C# are 32-bit long. So this number here should be all ones. Now, if I left shift this number by one step, what I expect to see is 31 ones followed by a single zero. But what should happen when I right shift it by one step? Well, let's find out. So notice that when I shifted it to the left, I pushed in a 0, just like before. But here, when we shifted it to the right, all these bits, although it's hard to see here, are actually moved to the right by 1. But then what happens is that because we have told the compiler that this is a signed number, when we right shift a signed number, the convention is that the most significant bit, the bit that says this is a negative number, is copied. So these ones get copied, and thus this number retains its signedness. I think this becomes more clear if we start with a small with another number, namely the most negative integer, which is int min value. Now this number is, if we represent it, well, let's just write it out straight. And then we're going to shift this to the left, and then we're going to shift it to the right. And let's see what happens to this number. Now, the most negative number in 2's complement is always going to be a 1, which is the sign bit, followed by all zeros. So let's see what these numbers look like when we represent them in binary. So here you see the most negative number. And as you can see, it's a 1 followed by all zeros. This is the most negative number that can be represented in 32 bits in 2's complement. Now, if we shift this to the left, however, that single 1 gets pushed out of the word, and we push in a 0 at the beginning or the least significant end of the word. And that results, of course, in a 0. But if we shift this number to the right by one step, what happens here is that the sign bit gets copied. So this 1, the one to the right, is the original 1, the sign bit. And then by doing this right shift, we maintain the sign of this word. But sometimes this is not what you want. Sometimes you want to shift the word to the right, but maintain a 0 at the most significant bit. And in order for this to happen, in C# there are two ways of doing this. One way is to say, I want this number to be treated as an unsigned integer. And an unsigned integer is just a convention. We've just told the compiler, please treat this as this bit pattern as an unsigned number. And so what I'm doing now is I'm taking my unsigned value, which we used before, and I'm just forcing it to become an unsigned integer. This doesn't change the bit pattern. The bit pattern is still just a 1 followed by all these zeros, as we shall see. But the behavior when we shift to the right now changes. So let's watch. In fact, maybe we should compare the two by keeping the original. So we'll do this. So this is the signed representation, and this is the unsigned representation. And we'll call this U because we can't reuse the variable. All right. So let's run this. Let's resize the window a little bit so we can see what happened here. So in the first case, the signed number, just like we did before, this is the maximum number. Notice that by treating this bit pattern as an unsigned integer, the pattern itself did not change initially. It's just a bunch of bits starting with a 1 and then falling with a 0. And the left shift behaves the same way in both cases. We got that high bit pushed out of the word and replaced the lowest bit with a 0. That ends up becoming a whole pile of zeros. So in both cases we get a 0. But in the unsigned case now, when we shift to the right, Notice that this number here is actually shorter. You should think of this as a leading 0 not being printed here. There actually is a 0 in front of that 1. So an unsigned integer, when shifted to the right, it will always inject zeros at the most significant bit position. So there's a key distinction between a signed number and an unsigned number. But again, this is only because of a convention that we've made. We've made the convention that when performing a right shift on a signed number, we're going to duplicate the most significant bit position. But when we're right shifting an unsigned number, the convention is that zeros are injected into the most significant position. Okay, great. So we've talked about shifting. We've talked about the use of a mask using the AND operator. Now let's show you a little trick that becomes very, very useful when building these masks. So let's take a number like this number here. So what is this number? Well, this number is 1000 in binary representation. It's just the number 1, the digit 1, shifted left three positions. Now if I take my n here and I then subtract 1 from it, what happens? Well, if you know your binary, you know that the resulting 7 is going to look like this. But for me as a low-level bit hacker, the more interesting effect is that I started with a number that had 3 zeros and a 1, but now I have a number that consists of that many number of 1s instead of zeros. And this, in fact, is a mask of 3 bits. So if I wanted to create a mask, I could say, take the number 1, shift it to the left by the number of bits that I want my mask to be, and then subtract 1. So this could be made into a function. So let's do that. So here's my function mask, which, let's make it static, which takes a number of bits and converts that into a mask. So now if I wanted to write these out, let's write mask, 1-bit mask. Let's maybe write out a 4-bit mask and I don't know, a 16-bit mask. Let's see what that looks like. Alright, so here's our 1-bit mask, here's our 4-bit mask, and here's our 16-bit mask. So this is really convenient because now we can, with this simple function mask, we can create a bit mask that we can then use to extract bits out of words like we did before. But we can do more than this. We can also say, I want to take, let's for instance, if I have a word that looks something like this. I have 5 bits in the beginning, and then 3 bits in the 3 bits in the middle, and then 8 bits at the end. And I want to write a function that extracts these 3 bits, right? Let's make them more distinctive by making them 100, for instance. So how would I do this? Well, mask gets me halfway, but I first need to take those bits and shift them down to the bottom so that they become the least significant bits in the word. So to do that, what I need to do in this case is to shift them to the right by 8 bits. And then I do the mask. So let's create another function called bitfield, which given let me take a step back. I went ahead of myself. So what I can do now is take this let's call this int n, or uint n, it doesn't really matter. So there's my data, and I want to now extract these 4 bits. So what I'll do is I'll take my number n and I'll shift it to the right by 8 bits. So what that will do is position these 3 bits at the very bottom of the word, discarding all these ones below them. And then I'm going to use my mask. Let's change this to an int for now. And use the mask of 3 bits. Now that should result in the value 100. So let's confirm that. Let's see, there is a complaint. I'm not sure if that is a real. Let's give it a try. Sometimes the Visual Code Editor doesn't behave as I expected, and it's giving me an erroneous error marking here. But our program compiles, and as we expected, the 3 bits that we wanted to extract from the middle of the word, they were correctly extracted in using this expression. So we take the number, or the encoding, the bit pattern that we want to examine, we shift it left or right by the number of bits to move the relevant bit field to the least significant position, and then we use a mask to extract the bits that we care about. Now this can all be extracted, and if you are a fan of the Reco decompiler project, you will have seen how all of the disassemblers in that project use the following standard class to represent a particular bit field. We're going to create well, let's make it a struct. It could be a class as well, but let's just make it a struct, and then we're going to call it a bit field. Now the bit field will encode the notion of a bit field in a word. So what we want to do is, when we create a bit field, we want to give it a bit position, so position, bit position, and a bit width, the number of bits that we want to extract. And what we're going to do is we're going to pre-compute the mask. So we'll say this.mask equals the 1, right shifted to the bit width, and then subtract 1, just like before. And then we'll record the bit position as is, just like that. All right, so let's create these fields. Let's make them read-only, because we don't like mutable structs. And then now with a bit field, what can we do? Well, we can give it an integer which contains a bit pattern and ask it to extract the value. So we can say extract, and we give it a mass or a value, so a bit vector, just a bunch of bits. And so what we want to do then is take the bit vector, right shift it by the bit position, and then return this shifted value masked with the mask that we pre-computed in our constructor. So now we have a class where I can say, here's a bit vector, and I want to extract a bit field, and we're going to specify that the bit field is at position 8 and has a width 3. And now I can say bit field, extract the bits from the number n. Now this should give the same result. We have 3 bits, and the bit field corresponds to position 8, and then the 3 bits starting at position 8. So we should still get 100 as a result. Okay, so let's try it. Let's see if it works. Awesome. So now we have an abstraction of a bit field, and this will come in very, very handy next time when we start building our full-blown Risc-V emulator. But before we stop for now, let's have some fun and let's implement control flow in our little pseudo emulator. Now, what we want to do is use our newfound knowledge, in particular this capability of representing negative numbers, in order to represent looping, that is, jumping around in our program. And in order to accomplish this, what I'm going to do, let's first of all, let's clean up a little bit. We're going to take our bit field and we're going to move this into a separate class because I know that we're going to be using this at a future point. So let's create a new file called bitfield and store this guy in here. There's our... Did we lose everything? What happened? I am not sure what's going on here. Oh, I'm just being confused by the fact that it's collapsed. My mistake. Let's do this again. Or cut, paste. There we go. So now our bit field is safe in a separate file. And now we're going to bring back our assembler. But before we bring back the assembler, let's just write a simple function that does a loop. And I can think of one. It's called the factorial function, which is a very popular way to introduce people to computer science topics. And in this case, we'll just write it in a simple C# manner. We'll say we have an integer result, which is the factorial, and we initialize it with a value 1. And then what we're going to do is we're going to say we have this number n, which is going to be the number whose factorial we wish to compute. And we will say while n is larger than 1, we are going to take the result and multiply it by that number, and then we're going to decrement the number by 1. And then we repeat this until n becomes either equal to 1 or less than 1. The factorial, by the way, is defined to have the numeric value 1 when you give it the value 0. So 0 factorial is 1. And let's not worry too much about negative numbers. So let's define the number n, and n is going to be the number 10 in our little example. Okay, so here's our program. And if we run this, we should expect a value which, if I recall correctly, is something like 30 million. But let's see. Let's write our result like this, and there's our number. Okay, so it's a little bit. It is 3.6 million. Fine. So, how do we make this into our assembler language? Well, let's simplify the code first of all. Now, this while loop can be broken up into gotos. Now, some of you may not be familiar with gotos because they are frowned upon when programming in high-level languages, but C# does have goto, and we can use gotos to represent this loop. So what we can do is do this. We'll say goto check, and then we'll create a label check, not checked, check. And then we say, let's get rid of this, and then we say while n or not, let's get rid of the if, and we say if n is larger than 1, go to loop. Okay, you say now, what on earth is going on here? Well, let's just follow the code. It's quite simple, really, once you get used to the new syntax. But these two lines of code execute as before. Then we're telling the C# compiler, I want the control to go to the part of the program that has the label check, which is down here. We check to see if n is larger than 1, and if it is larger than 1, we go to the loop label. And this loop label will then perform the computation just like it did before, and then control will fall down to the same position, check, and it will check the loop condition. If that is still true, then we continue looping, and we repeat this until we fall out of the loop. So we haven't really changed the meaning of the program, we've just changed the way it's expressed. And if all goes well, then this should still give us 3.6 million, 10 factorial. Okay, great. So if you remember the previous sessions, you will recognize a lot of these simple additions and subtractions that we're doing, and the multiplication, they can all be represented in our assembler. So we'll do the same procedure that we did last time. We're going to take all of our variables and give them register numbers, and then we're going to represent these assignments with the add I instruction, and then we're going to use a multiplication, and we're going to use an addition with a -1, but then we need to handle this. So we don't know how to do this yet, and that is the focus of the remainder of the session. So let's start by converting or creating an assembler. We'll need an assembler, so let's do that. We're having our assembler, and it's going to be a new assembler, and we don't need any parameters for it. Great. And then the first instruction, well, let's change everything to register. So this is going to be x1, right? And this is going to be, let's call this x2. Are there any other? There are no other variables. That's good. Okay, great. So this initial assignment is the operation is going to be add I, and we're going to put the result in register 1, and we're going to add the contents of register 0, which, as you remember, always has the value 0, and then the value that we're adding to 0 is 10. And this results in 0 plus, well, the contents of register 0, which is going to be 0, plus 10 being stored in register 1. And similarly, for register 2, we're going to put 1 into that register. Great. Now we have this new instruction, go to. We don't have it yet, so let's just assume that it exists. And we'll have to use an @ sign to tell the C# compiler I want to use goto as a label. And we can go to here and add a goto. Great, so there's our goto. But what do we give it as argument? Well, let's give it the argument -1 for the time being, and we'll come back to this. And we need 3 arguments, so I'll just put in a 0 there to quiet this up. So now we've translated this sequence of instructions. The next one is going to be the body of the loop. So here we're going to say that the register 2 gets the result of multiplying the register 2, or the contents of register 2, and the contents of register 1. So that's going to be mul. Contents of register 2 get replaced with the product of register 2 and register 1. This is a little awkward. I'm going to rename this variable m, because it's a lot of typing and the double asm looks confusing. Okay, and then we need to subtract 1 from x1, which is the same thing as adding -1 to it. So Let's use an immediate add for that. So we'll take our 1, register 1. Its value will be updated with the value of taking the contents of register 1 and then adding -1 to that, or subtracting 1 to it. So now we've done the loop body. And then finally, we have to do the check. So, what we can do here is say that we definitely need a new kind of instruction. We need an instruction that performs a comparison and then tells us what the result is in a register. So let's introduce a new instruction called set if less than immediate or greater than immediate. There we go. So what this will do is it will set, and we'll need a third register for this, don't we? So we'll use the third register to store the result of this operation. We say in register 3, I want you to store the result of comparing the contents of the register x1 with the immediate value 1. That's what the I at the end of that instruction means. So what this will do is if the contents of register 1 is greater than 1, then we will put a 1 inside of the register 3. But if the number is 1 or less, and this is going to be a signed comparison, then we will put a 0 in register 3. Let's start with that. Okay, so now after that instruction we have a 1 or a 0. And so if we have a 1, now we want to go and back to the beginning of the loop and execute the loop. So we'll create a new instruction which we'll call branch, and it will branch, let's call it branch if not 0. In fact, let's abbreviate this to BNZ or BNZ. So if that register 3 is not 0, then we want to go to the label loop. But we haven't talked about labels yet. We'll wait until we're done with these two instructions. So SGTI, we need to create that as well as BNZ. So SGTI is 10 and BNZ is 11. Okay. And then for the BNZ, once a third parameter, we'll just add a unused parameter for the time being. Okay. But now we have these labels. We haven't really figured out the story of what these labels are. So let's just use a very simple scheme here. We're going to say that the label for we're going to translate these labels to instruction numbers. This instruction that the cursor is blinking on right now is instruction 0. This one is instruction 1. This one is instruction 2. And this one, which corresponds to the loop label here, is instruction number 3. Let's label this with a comment. This is 3, the loop header. And then this is 4, and this is 5. Now this 5 corresponds to the check. So this instruction here wants to go to instruction number 5. So go to, I'm not sure why we even have a 3 here. That's confusing. Let's just do that. So we're going to label 5, and then we're filling the other two fields of the go-to instruction with zeros. Don't cares. And here, branch not 0 wants to go back to the loop header, which we previously discovered was 3. Great. So what we've done now is we have implemented or well, represented our program using goto and branch not zero and this set greater than immediate instructions. Now we have to implement them in our emulator. So let's go to the emulator and go to the execute method, which is over here, and we're going to add now sgti. All right, so what this instruction is supposed to do is perform the comparison, and it's a signed comparison because we're testing against a signed number. So we will take the contents of source 1 and we're going to say if it's greater than the contents of the register source 2, if that is the case, then we want the result to be 1, otherwise 0. Now let's verify that these numbers are integers, they're signed integers. So this will result in a signed comparison. And then our flag, let's call this int flag. That's the result of our comparison. So if the register represented by source 1, if the contents of that register is larger than the contents of register 2 interpreted as a signed number, then we will put a 1 in the result. Otherwise, we'll put a 0. And then we put that back into the destination register, like so. Okay, that was sgty. Now then we have the goto. And goto now needs to somehow tell the emulator that we want to shift to a different instruction address. And so how do we do this? Well, exec right now has no notion of the current address, so we have to be able to specify how to execute these instructions and how to change the position in the list of instructions that we're executing. Now in the current implementation, we're just looping straight through our program, starting at position 0 and then just looping through one instruction at a time. We can't do that anymore. We need to introduce a new notion, which is the current instruction. So let's implement a variable called, we're going to call it instruction pointer. And it's not read-only, it's a mutable number, instruction pointer. And when we create our emulator, it will start at position 0. And then in our loop, what we're going to be doing is incrementing, instead of doing a for each, we're going to use the following loop construct. But now we have a subtle problem, and that is that this loop will always increment the instruction pointer, and that may or may not be good. So let's do this. Let's have the exec function as a side effect. It will, or as a result, it will return to us the new instruction pointer that we want to use. So let's change this to this, and then have exec return the next, the number of the next instruction to execute. Now the vast majority of our functions, they will want to just go to the next instruction. So I'm going to say iPutter equals iPutter plus 1, and then all of these will just return. Actually, we can live with this. That's fine. We'll change this to int, so that's going to be the returned value, and then here we'll return the new IPTR, just like that. And then all of these will work just fine. But then for our goto, we will now say IPTR is going to be the destination slot. Great. And then finally we have this new function bnz, and what it will do is it will conditionally change the instruction pointer. So what we're going to do first is check to see if the contents of the register in source 1 is equal to 0. So we say if the contents of the source 1 register is not equal to 0, then we want to change the IPTR to be instir.source1, which was, if you recall, the second value. So if this register 3 contains got to be careful here because the ordering is wrong. The destination is going to be register 3. Okay, so just remember this. The 3 here is actually the destination that we're jumping to. This 3 here is register 3. And then this 0 is the filler that we used. Although we yeah, it is a filler. Let's continue treating that as a filler. So so let's look at this a little bit more closely. So if we get a BNZ instruction and the register whose number is stored in source 1, if the value of that register is not 0, then we do change our instruction pointer to be the destination of that instruction. Otherwise, what we'll do is we'll just continue incrementing IPTR so we end up in the instruction following. So in this case, the B and Z will fall out to this next instruction index, which is also the termination condition for iPointer. If iPointer ever ends up outside of our program, then we just stop the program. Oh, we also have to fetch the instruction from our program. So we'll say program or insert equals program at IPTR, like that. So in theory now, if we've done everything right, excuse me, this should execute factorial. All right, let's give it a try. And indeed, it does. It worked the first time. I am surprised and humbled and awed. But let's go back to our program now. So if you recall here, we're going to be adding the immediate value 10 to the register value inside of register 0, which is always 0, thus giving us the number 10. That gets stored into register 1. Then we do the same thing. We take the immediate value of 1, we add it to the contents of register 0, which is always 0, thus giving us the value 1. Then we go to label 5, which is down here. This is what corresponds to check. Oh my goodness. I spoke too soon. This is not correct. This is our original program. What we want to do is display the contents of register 2. So we need to say I spoke too soon. We have to create an emulator too. So let's create an emulator with the assembler program and our memory, and then what was the method called? Exec. All right, and then what we want to do is take a look at the emulator's register number 2. All right, now we try this. The joys of live coding. Oh, and we have a bug. What's the bug? Here's the bug. We are... No, looks good. We are multiplying the register 2 with register 1, and that gets stored in register 2. All right. So now we have to debug this. Oh, how fun. It could be that the goto instruction is not working correctly. It could be that the sign comparison is not working correctly. So let's debug this. We'll put a breakpoint on the exec function, and let's see what it does. Right here. And let's run this. So this is going to be the add immediate. We know that those work, so we'll just skip those two. Now here we get to the current opcode is 9, and opcode 9 is the goto. So the goto should now change the current instruction to, well, one that has label 5, which is the check label. So let's evaluate this. Destination is 5. Good. So now we're on instruction number 5. Now we read that instruction and we try to execute that. And I have to pause. Sorry guys. I'm getting an inbound call that I cannot ignore. So we'll have to pause and continue later. Alright guys, take care.